Good evening, everyone. I'm Yogi Joshi. I'm one of the members of the Real Time Embedded Software Group at the University of Waterloo. And today I will be providing you a demo of Rhythm Tool. Rhythm Tool is runtime time triggered heterogeneous monitoring tool which takes a C program along with a set of LTL properties as input and generates an instrumented C program which can be monitored at runtime. In this case, we consider a monitor which has a fixed polling period. So we start with this demo and we need to provide the tool with a C program which we want to instrument. So this is a simple program which generates a Fibonacci series, and we may want to monitor certain variables in this program. So let's consider the set of LTL properties and associated predicates. So the first predicate is this, which suggests that the value of the variable I should be greater than 10, and the property is that this predicate should be eventually true when a program runs. Next predicate is value of variable I should be less than or equal to n, and the associated property is that this should always hold true. Now in this program we can see that I would eventually become greater than 10 because I is used in the loop as a counter and value of n is 30, and we increment I until this condition is satisfied. So I would eventually become greater than 10. However, I would become greater than 10 after the loop terminates. So this property associated with this predicate may not hold true. The third predicate is that f new should be greater than f old. These are the variables used to generate the Fibonacci series. So f new would usually be greater than f old. However, f new may not be greater at the initialization stage because here we don't have any initializers. So we can monitor this at runtime whether this property is satisfied or not. Now let's run the tool over this input. So we have to provide the tool with the source path. So I'll provide the path of the Fibonacci series source code. Further, we have to provide the path of the output directory. So this is the directory in which we will get the instrumented source code. The third path is the property file path. So this is the file which holds all the LTL properties. Further, we are using fixed polling period, and we are using sequential algorithm, which means we will process the program state variables sequentially. Invocation type is synchronous, so our monitor will be a blocking monitor. The next option is the target polling period. So this is the frequency with which the monitor would be invoked at the runtime. So I will provide 19 cycles here. Next is the buffer size, which means the size of the buffer which is used to hold the value of the variables which we want to monitor. So I'll specify 1000 bytes, and this is the flag we use so that the program, when it is run, it will log the value of the variables to a particular file so that we can have a backtrace to determine where a particular property was validated. So I'll run the tool. So here we can see that the monitor generation is successful, and we can now get our instrumented code in a particular directory. So this was our output directory, and here we can see the instrumented source code. So here we can see that the program is instrumented, and there are different instructions added to this program which will ensure that the program state, that is the value of the variables which we want to monitor, is sent to the monitor program. So let's now run the let's now compile the code and run that. So now I have compiled the code and I'll run that now. So here we run our instrumented code and now we can see the log file. So this log file is rhythm trace, so which will show us whether the properties were satisfied or not, and it can also show us the backtrace so that we can determine at which line a particular variable was modified, and from that we can determine where in the program the property got violated. So this ensures us that we can determine the cause due to which a particular property was not satisfied. So let's run the view log. So this is a complete log of the Fibonacci series program. So it shows us here that property 0 was satisfied. So let's see the property 0 here. So the property 0 was that I should be eventually greater than 10. Eventually I should become greater than 10. So in the trace we can see that and in the trace we can see the values of all the variables and the line number at which a change occurred to their values. So we can see that this is a variable I. First is the line number. We generate a CSV output here. So at line number 14, value of I was changed to 0. At the same point, the value of event n was 30 and values of other variables are also shown. So we can see that the second column is the value of variable I, and we can see that eventually I has become greater than 10. So we can verify this property at where the variable value was modified. The second property is I should be less than or equal to n, and this should always hold true when the program runs. Now this property is shown to be violated because value of I has become 31 while the value of variable n is 30. This has happened when the loop got terminated. Now the third property is that f new should be greater than f old, and this should always hold true. We can see that here there are no initializers, so we don't know about the initial values. So let's see the trace, and this property is shown to be violated, and we can see here that these two columns show the values of f new and f old, and at the beginning the value of f new is 0 and f old is 0. So at the beginning itself the property got violated. So this is the way we can determine the cause or the instruction which changed the value of a particular variable, and we can monitor the values and determine the issues in the programs by using this tool. So that's it. Thank you very much.